Now the nano world, scales of maybe 10 to the minus 7 of a meter, is dominated by random thermal motions, by heat energy. That's what we're going to talk about now for quite a while. It turns out to be the basis of thermodynamics. Now we often hear that heat is described as atoms jiggling around. The faster they jiggle, the higher the temperature. But in reality it's a little bit more subtle than that. Let's say we have these atoms here, and as you can see they're all moving, but they're all moving pretty much at the same speed in the same direction. So this might be zooming in on a little bit of a ball being thrown through the air or something like that. Now you wouldn't analyse this with thermodynamics, you'd analyse it as projectile motion, a ball throwing through the air. We know how to solve that sort of problem. If, on the other hand, we zoom in on something and the atoms are going like this, now they're all going in different directions. Now this is not going to be projectile motion. In principle, what you could do is solve for the motion of every individual atom, but that would become too complicated. So this, where everything is going at random different directions, would actually be a case where you'd analyse it using heat and thermodynamics, and we'll come to how we do this later. Those are the two main cases. There is actually a rather fun intermediate case, something like this. Now here you can see things are almost but not quite random. Things are going in different directions, but all the ones on this side are going down, all the ones on this side are going up. And this is what we'd call turbulence, and this is very hard to solve. It's not quite disordered enough to treat as heat, it's not ordered enough to treat as projectile motion. It's an intermediate case, it's very difficult. And in fact, typically most motions go through this. So let's imagine, for example, you blow some air out of your lips. To begin with, the air goes nice and smooth, like projectile motion. Then it starts going into eddies and billows, like turbulence. And eventually, after you finish off, it just ends up as random thermodynamic motions and heat. This is called a Kolmogorov cascade, and is a common process whereby ordered motion turns into disordered motion. Now in reality there's no fundamental difference between random thermal motions and ordered motions. The only difference is one of complexity. In principle, you could treat heat as just by solving the Newton's laws and projectile motion for every single atom in a body. But even a small object like your thumb could easily have 10 to the 23 atoms in it, so that becomes computationally totally impossible, even if you could measure where they all were at the starting time in their motions. So we have to use some sort of statistical approach to deal with it, and that statistical approach is called statistical thermodynamics. The fundamental idea is that anything that's not at the temperature of absolute zero, the atoms are moving around and have energy. If you've got a monatomic gas like hydrogen, normally hydrogen can be diatomic, then all this energy is in the form of the kinetic energy of the different particles moving in different directions. If you get a diatomic gas like air, which has things like oxygen and nitrogen, which are molecules with two atoms, then these molecules are also moving around, which is some of the energy, but also they can rotate around their center of mass, which is another form of energy, and they can vibrate. You've got to imagine that the bond between two molecules is like a spring, and so you get the atoms vibrating back and forth on the end of a spring. And so in this situation, the heat energy is not just the motion of the molecules, it's also the rotation of the molecules, the vibration of the molecules. If you have a solid, you've got to imagine the atoms are bound by chemical bonds to other atoms in some complicated structure. And here the atoms are not free to move around by themselves, but they can vibrate vertically, horizontally, and in and out of the screen. And that tends to be the dominant form of energy. So all these sorts of motions, and also the potential energy in the spring, are forms of heat energy. They're all types of internal energy that is too complicated to deal with one at a time. In principle, in any of these situations, you could just treat each atom and solve its rotational motion or the vibration of its spring. But again, we're talking 10 to the 23 atoms and even a small bit of gas, so that becomes infeasible, and we have to deal with all these motions statistically. And that is the basis of statistical thermodynamics.